Good. Well, thank you very much for the opportunity to talk to you about this. I've been following some of the lectures from afar, and it's been an interesting, very interesting workshop, including last week. And that I'm sorry I couldn't be there. I should also apologize in advance that there's some builders.
You are not clearly audible. Can you please?
Okay.
Increase the volume.
If this work, does this work any better?
Yes, it's better now.
Okay. So just wanted to apologize that there are some people working, some builders working on the roof above my office today, it turns out. So I hope they won't be too loud. So you've already heard a fair bit about the idea of rate-induced tipping and a little bit about non-autonomous systems. So I want to go a little bit more into that and some specific examples that I've worked on in the past few years. So I'll talk a little bit about tipping as a phenomenon that really appears only when you start to look at non-autonomous systems. And of course, non-autonomous dynamical systems are quite different beasts to autonomous dynamical systems. So autonomous dynamical systems, you can look at invariant sets, and you look at their hyperbolicity, their stability and bifurcation, and that tells you a lot about what goes on. With non-autonomous systems, they can be really bad in a lot of ways, and in particular, they don't usually have invariant sets in the sense of a set of phase space which is fixed, and that causes some interesting issues. Yeah, I'll talk a little bit about that, and I'll talk about bifurcation, rate-induced tipping, in particular in one dimension. I don't think Sebastian went through the paper that we did with Perryman in 2017, so I'll look at some examples from that. Then I'll talk a little bit about tipping from periodic attractors. So this is work with Hassan Al-Qayoun from a few years ago. It was his PhD thesis. And then I'll talk a little bit, see how far I get on extending these ideas to higher dimensions, in particular R-tipping, rate-induced tipping from equilibria in higher dimensions. Maybe a little bit on discussion at the end. I don't know if I can get rid of this thing. Let me see if yeah, okay, good. If you have a dynamical system with time-varying inputs, that's what we call a non-autonomous dynamical system. And if you think of the inputs as parameters, you can think about it in a number of ways. You can think of this as a parameterized family of dynamical systems. As I change the parameters, the set of attractors will change. If you go through a bifurcation, then it's clear if you were sitting on that attractor that is bifurcated, then something's likely to happen. And the idea of the bifurcation-induced tipping is you have slow passage through some sort of bifurcation where a parameter changes. That parameter changes slowly relative to the system dynamics, whatever that means. I know Peter Cox was talking a little bit about timescale separations, but if you have a good timescale separation between the dynamics and the behavior of the parameter, the behavior of the forcing, then bifurcations tell you an awful lot about tipping points. If your input, however, is maybe small amplitude noise, but has occasional large deviations, extreme events, then that's another type of tipping that we've called noise-induced tipping or noise-induced escape. This has been studied a lot in the past under different names. Things like stochastic resonance relate to this. The one which I'm going to be focusing mostly on is, however, rate-induced tipping. That starts to appear where the time variation of the input is of a comparable timescale to the timescale of the dynamics of the system itself. And in that sense, they're sort of genuine non-autonomous instabilities. And in a sense, you could see this as trying to mine the bifurcation diagram of the parameter fixed system for more information than it should really give to you. And this is the paper with Peter Cox, Renato Vitolo, and Sebastian Wieczorek from a few years ago. I've got the references at the end if you're interested. So here, just a sort of a little figure showing the idea of the difference between the bifurcation and the rate-induced tipping. For the bifurcation tipping, no matter how slowly you go over the bifurcation point, you can reach a critical level of some external input, and you get a sudden change driven by the dynamics. In rate-induced tipping, you have a problem when you go too fast to track a moving stable state of some sort. Okay, so the setting that I'd like to talk about is the case where you have a dynamical system that is described by differential equation in time, where you have a state variable x and you have an input lambda which depends on time, and you can either consider this like a family of parameter paths where you parameterize this in some sort of arbitrary way, but we found it's been extremely useful to parameterize it in a very particular way, just by basically scaling the time of how the parameter varies. That then you can connect your understanding of the system dynamics in the limit as r goes to 0 using sort of singular perturbation theory. So this is the non-autonomous system. You have a family of associated autonomous or frozen systems that correspond to you just fix the parameter and then let time run off to infinity. So there's a very well developed theory of non-autonomous dynamical systems. In particular, written down, there's a book by Kloden and Rasmussen from a few years ago, an AMS textbook that comes up with some very clear ways to handle the dynamics of such systems as this non-autonomous system. So in particular, if you evolve forward starting at some point, let's say x0 in phase space, in an autonomous system, where you end up only depends on the time elapsed. But on a non-autonomous system, it depends on the starting time and the end time. And so the dynamics depends on two time-like variables. If you start at some point x0 at time s, and you evolve forwards to some time t, that gives you the new location on the orbit. So this is no longer a flow, but it's a solution co-cycle or a solution process that satisfies this sort of equation. So if you start at time u, go forwards to time t, that will be the same as if you start at time 2, start at time u, go forwards to time s, and then from time s on to time t. So I should really highlight that there's a very well-developed theory out there. I'm not really going to talk about it very much, other than in a quite a limited way. And again, general non-autonomous systems are very difficult beasts to deal with because they're always sort of, nothing is fixed in them. So a particular family that we've looked at in some detail are those which we call parameter shifts, which start and end at some sort of limiting system. So they start as time goes to minus infinity. They'll always start at some parameter lambda minus. As time goes to plus infinity, they'll limit to some lambda plus. And so you have a well-defined notion of a past limit system and a future limit system if you have such a parameterization. So this is not the set of all autonomous, non-autonomous dynamical systems. This is a very limited set, but note that the dynamics in the past and the dynamics in the future can be really quite different. Okay, so I reckon you've been sitting in this lecture theatre for a very long time, listening to talks, and I thought I might do a little bit of audience participation, just to get a little bit of feedback from you, because it's very difficult giving a lecture when you're thousands of kilometers away. So I don't know if you're used to using menti.com. So if you have a device there and you put in menti.com and put in this code, and don't worry about the code will stay at the top for the next few minutes while I go through this. So now I should be able to go on to the next slide here. Here we are. So there's just a number of short questions where I'd like to help get some picture of where you are at the moment and what your concerns are and what your background is. Hang on, I think I missed a question, haven't I? Yes. So firstly, there should be a question about this. I don't know if you can log into this menti.com and type in a few things, and then a word cloud should appear of the sort of things that maybe you're all doing physics, but maybe not. Zoology, interesting. Mathematics. The size is sort of proportionate to the number of people who early warning signals, yes, okay. Quite a few ecologists. How many people in the room? There's about 1, 2, 3, about 30, something like that. Okay. Critical transitions, okay. Very nice. Okay, that looks about good. So, yes, mathematics, physics and ecology. I'm interested to see there are quite a few ecologists, but of course, critical transitions is something that's particularly important for you. Okay, so I've now got a question on sort of what is your particular interest in tipping points. So a few questions coming in there already. That's a few comments. Okay, yeah, forecasting, early warnings, ecosystems, real time, prediction, yeah. Oh, someone, there's an engineer there, that's great. Transition seasonality, I guess that's the an ecologist. Okay, very good. So I'll just go on to, I think, what is the last question maybe. I'd be interested, so not related to what you've heard so far, or what you think you're going to hear. Are there particular things that this workshop may inspire you to do? I think this is like a free text thing. Yes, tipping points in climate is a particular area that I'm working with collaborators in, and I think you've probably heard quite a bit in terms of the other talks. You've got, you had Peter Cox the other day, you got Tim Lenton, Valerie Levina, I saw give a talk a couple of days ago. It sounds like there's something very large going on, jumping up and down on the roof now here. Oh yes, tipping points in spatial systems and in real world systems. Yeah, okay, definitely read more about non-autonomous dynamical systems. That's a good thing. Okay. Very good. So thank you for that. I will share the output from those slides with the organisers afterwards, in case you want to have a look again. Okay. Good. So we get back to parameter paths. So here are a couple of examples of parameter paths that parameter shifts in one dimension from, in this case, we limit to -2 in the past and +2 in the future. And in fact, this is two ways of doing it. One of them is doing it monotonically, one of them is doing it non-monotonically. And one of the interesting things we noticed was that actually whether this is non-autonomous or whether this is monotonic or non-monotonic actually can make a difference in what sort of behavior you get. More of that in a moment. So a little bit of sort of terminology from non-autonomous dynamical systems. The problem with non-autonomous systems is that there is more than one notion of time going to infinity. You can either sit with some initial condition and you go forwards in time off to infinity, but then the problem is you're trying to hit a moving target. And so if, for example, you define your attractor in this way, this is like a forward attractor, it's rather difficult if your forward attractor is actually limiting, doesn't have a well-defined sort of limit. It can maybe even its dimension is not, sort of the set of limit points of the forward invariant set could be really quite wild. And so when we're talking about attractors, we often talk about pullback attractors. A pullback attractor is, roughly speaking, it's the set of points you expect to be at some point, given you started a long time ago in the past. So in that sense, we're saying if we take the limit where we fix the time, say t, to be present, and then we consider the limit as a time, in this case -s, goes to infinity. So let's look at the technical definition. Suppose you have a solution of a non-autonomous system. So this is like a time parameterized path in phase space. This is a pullback attractor, a local point pullback attractor. If there's a bounded open set and a time such that for all times sufficiently far in the past and any initial condition in U, and all points starting in that neighborhood limit to X as you pull them far enough back into the past. Now, there are a number of issues with this definition already. This is a fairly standard definition. In particular, what you might want to do is consider if you have a really non-autonomous system, then a stronger definition of a pullback attractor would be, or a more useful definition of a pullback attractor would be to say we're actually going to consider a neighborhood that also changes with time. The problem there is that you can have crazy things happening in that the size of your neighborhood can shrink to 0 as you go backwards in time, although it's a neighborhood. And in fact, you can end up with something like a repelling fixed point being an attractor in that sense, which is just a bit too weak. So here's the theorem. This is from a paper with Claire and Sebastian, 2017 in nonlinearity. So suppose you have a point on your bifurcation diagram. So this is a state, and this is a parameter on a branch of stable states. Then there is a unique trajectory for the non-autonomous system that limits to this point as time goes to minus infinity. That's for all R, and moreover, this is a local point pullback attractor for the non-autonomous system. So that means that you can, if you have a parameter shift, you have a number of attractors in the past limit, and for each of those attractors in the past limit, in fact, there is a non-autonomous pullback attractor that is sort of rooted in that, and that's the notation we use here. So given the parameter shift, the rate, and the attractor in the past, there is in fact a unique pullback attractor. This is true in 1 dimensions. More on higher dimensions, it gets quite a lot more messy quite quickly. So first question is, when does the pullback attractor track a stable branch within the bifurcation diagram? And if not, does the pullback attractor limit to another branch of attractors? And in fact, could the pullback attractor even be a forward repeller? And this is actually a definition that we use essentially for rate-induced tipping. It's when a pullback attractor is a repeller in the future. Okay, and what sort of transitions are possible and generic as we change the branch? So here's an example. Here's a bifurcation diagram we cooked up. This is in the paper, the 2017 paper, where you have a parameter here, lambda, you have a state variable x, and this is set up so you have a number of stable equilibria, stable branches here, 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 and also on the other side. And then you also have a number of sort of pitchfork bifurcations that face each other. These are all supercritical pitchfork bifurcations. And the red is an indication of, if we consider the trajectories that start in the past limit at this attractor, where do they end up in the future limit? Well, in the absence of noise, in the presence of sort of a perfect dynamical system, if you start up at 0, as you go forwards, you're still at 0. So in fact, there's something rather funny going on here, owing to the fact you've got a bifurcation sitting on your pullback attractor. Okay, if you add a small perturbation either to the initial condition or you add noise, then starting at this stable state in the past, as we go forwards, we'll end up either at this state or at this state, and there'll be a sort of a 50-50 choice if you had symmetric noise. However, that's just for the case where we have a monotonic parameter shift. If you remember here, if I consider a parameter shift of this form, then we can say with some confidence, well, even make statements with almost sure, that we will end up in one of these two cases in the limit of small noise. If I go back to the non-monotonic parameter shift, however, it's a bit more interesting, because you notice this overshoots 1 and then it undershoots -1 and then it comes back to +2. So in that second case, what will happen is I will come up to here, and then as I come back, I may actually flip onto this branch, and then as I go forwards, I could end up even up here or down there. So already with sort of non-monotonic parameter shifts, you can get some interesting behavior. So in 1 dimension, you can really characterize criteria for bifurcation-induced tipping and indeed for rate-induced tipping fairly precisely in terms of properties of this pullback attractor. Okay, maybe I'll just skip over that. I hope you can still hear me. There's a noise going on the roof. Yeah, good. You can hear me, I hope. So I want to move on to this example.
I can hear you clearly.
You can hear me, very good. This is another example where the bifurcation diagram is a bit more complex. So you have a stable branch shown here in black. You have another stable branch y plus, which is shown in black, and then an unstable branch somewhere in the middle. In the presence of a low rate of monotonic parameter shift from -1 to +1, in this first case, you can see we track the stable branch, which is continuously going from x minus to x plus, and there are results that say sort of if you have a branch, then you go slowly along it, then you will always track it for sufficiently slow behavior. If I go a bit faster, you can see we end up on the wrong side of this saddle, this repeller here in 1 dimension, and this can actually send us off to a different equilibrium, a different stable branch. And somewhere between these two, there is a rate, let's call it R1. What will happen there is that the pullback attractor starting at x minus will limit actually to this repeller in time goes to plus infinity. That's like the separatrix between these two behaviors. But this example is interesting in that actually, as not the end of the story, if I speed up the rate even further, then I just skate over this region, and this is the sort of thing that Peter Cox was talking about, Paul Ritchie's work on overshooting a tipping point, the same sort of effect that if you come back fast enough, in fact, you don't really notice that there was another branch there. So tipping back, there's another case where between those two, there'll be a pullback attractor that is rooted in this single attractor in the past, and in the future limit comes back to this this unstable point. Okay, so let's make it a little bit more complex and start to look at what can happen in 2 dimensions. Of course, an awful lot of tipping is really about 1-dimensional dynamics. You have a saddle node, you're on some center manifold or something like that. But suppose you have a branch of attractors that is uniformly stable, not necessarily a point. The previous case was just one trajectory. A more general pullback attractor will be infinitely many trajectories. There's a similar sort of result. This is in a paper with Al-Qayyum, where if you have a branch of attractors, then under some assumption that it's quite strongly stable, uniformly stable on some parameter interval, then for any parameter shift between lambda minus and lambda plus, the pullback attractor will track this for small enough r, in the sense of sort of Hausdorff distance. So here's a particular example that I'd like to go through. I think the higher dimensions I will probably not get very far into, but I understand Sebastian's coming back to tell you more about that tomorrow. So this is an example where we have, this is a 2-dimensional phase space. You can see that this is a sort of Hopf normal form, where it's like a Botan bifurcation normal form. You have a case where A is going to be positive, so that means you have an equilibrium at the z equals 0 in the complex plane that is unstable, and then the alternating signs on these and A being small enough means that you have a stable periodic orbit and an unstable periodic orbit surrounding it. And we'll consider this parameter shift, which goes from 0 to 8 in this case. Hopefully this will work. So here is a simulation. The top shows you what's going on in phase space. The bottom is showing you what goes on as the parameter changes. So here, this is time along the bottom. Hopefully it will repeat, yes, and the red dot shows where we are in time. You can see the lambda is changing monotonically, and that just moves the attractors for the frozen system. It's basically, the attractor is just this green limit cycle. So that's just translating along. We've got a region here which is an unstable periodic orbit, and so the basin of the stable periodic orbit is precisely the frozen system. Everything that is inside the red dashed line, and we've got a repeller which is the X black X in the middle. And what we're doing here is we're starting with a, if I stop maybe near the beginning and move this back, we're starting with a random set of initial conditions chosen within the basin of attraction. And you can see they very quickly head towards the pullback attractor, and the pullback attractor is close to, but not quite at, the location of the attractors for the frozen system. So I should say, I've been looking at more recently with Julian Newman. There's actually a notion of physical measure on these attractors as well. It's roughly speaking, if we start with a cloud, a Lebesgue distributed cloud of initial conditions, then there's a physical measure is actually a measure on the fibers of the pullback attractor. But okay, so this is an example where you track the attractor. You can see that in the past and in the future, the pullback attractor is limiting to the attractors for the future and past limit systems. If we now go a little bit faster, so this is at a higher, going at a higher rate, you can see this is a slightly steeper than before. Oh, if I freeze here, you can see that some of the initial conditions have ended up on the wrong side, outside the basin of attraction, and they go off to infinity. So what you end up with is a scenario where a positive probability set of points on the pullback attractor track the branch, but also a positive probability set go off somewhere else, and this is what we call partial tipping. And this is probably a very common thing that will appear in high dimensional systems where you have, for example, chaotic pullback attractors. And in the case of total tipping, dealing with time, yes. So now we've upped the rate a bit more, so there's an even steeper whoop, and now all of the initial conditions have gone off somewhere else. Okay. We can understand this using the technique of compactification, which I believe Sebastian will tell you more about. If you have a non-autonomous system that has autonomous limits, it turns out that you can always extend your dynamical system to a higher dimensional system, one higher dimension, by compactifying time in a particular sense. So this is showing sort of schematically what's going on. We've got an attractor here for the past limit system in the compactified sense. This is now in 3 dimensions. We're in a 2-dimensional system. We've added 1 dimension. So this is the attractor in the past limit. This is an attractor in the future limit, and this is the stable manifold of the future equilibrium. You can find the unstable manifold of the past stable periodic orbit, and in the work with Al-Qayyum, we show in fact this is the pullback attractor in this case. In the case that you have a hyperbolic stable periodic orbit in the past limit system. You can also look at the stable manifold of the future unstable periodic orbit. This is like a pullback repeller. And in the case where you have tracking, so this is a case where you have a slow rate of change, you can see this blue sort of stocking in the middle is the pullback attractor. This is contained entirely within this threshold. If we look now at the partial tipping case that's here, this is a case where some of the trajectories on the pullback attractor limit to the periodic orbit, some do not. And in fact, you can locate the point sort of quite precisely where this will start as an intersection of manifolds. And this is shown by this very particular orbit here in yellow. We also have the rates, the critical rates where you go from tracking to partial tipping, and the critical rate where you go from partial tipping to total tipping, which is this case here, you can characterize as a particular type of codimension 1 connecting orbit. So in a sense, what we've done is shown that these mysterious rate-induced transitions you can understand as a bifurcation, but it's not a bifurcation of an invariant of an attractor. It's actually it's a global bifurcation of an extended phase space. So this is the parameter plane in this case. This is the rate against A. A was the the coefficient here. If we go back to this, so in this region we have tracking. Up to this point, this is where you actually get a bifurcation induced tipping, because the equilibrium becomes at this point the equilibrium becomes stable as you go on this side. On this side, you actually get a saddle node of limit cycles that destroys, and that's shown here in this section V. But you get a number of different, so you get a region here of partial tipping, you get a region here of total tipping. And if you look at the Poincare section, so you can sort of characterize what's going on here by taking a slice somewhere in the middle and drawing the pullback attractor that limits to the stable periodic orbit in the past, and the threshold that limits to the saddle periodic orbit in the future, and in fact they can intersect in a remarkable number of ways. So one can be entirely inside the other, or the other way round, and then the intersection with the equilibrium, with the stable manifold of the equilibrium, can be just about anywhere as well. That was quite a surprise for such a simple system. Okay, well, maybe I'll just say a few words about how this generalizes to higher dimensions. And this is a paper that's in preprint form at the moment with Sebastian and Chun. So now if we go to higher dimensions, but still limit to the problem of what sort of tipping can we get, and how can we identify tipping from equilibrium attractors, so still local point pullback attractors, there's no longer a sort of a well ordering. And so in particular, there was a notion of basin instability that we have in the 2017 paper that doesn't generalize quite so easily, but we have managed to generalize it in terms of thresholds. So we come up with a notion of a regular threshold, which is a codimension 1 forward invariant manifold that's normally repelling. So this is a purely autonomous concept, and a regular edge state is an attractor basically on a regular threshold. So there's this this figure gives you an example of the sort of things that can be an edge state and a threshold. So in this one on the left, we notice that there is, so this is a two-dimensional phase portrait. You have a stable equilibrium, you have a sink here at E1, and in fact, that's the only attractor in this system, yeah? Almost every point heads towards E1. But just because you have one attractor, that doesn't mean you have a non-trivial basin boundary. It's like if you have a fence in a field, that doesn't necessarily mean that there's two fields. It could be that it's the same field on both sides of the fence, and in fact that's the case here. So here we've got a saddle and we've got a repeller. If you look at theta, this basically the stable manifold of the saddle, this fulfills the definition of what we call a regular threshold. So locally speaking, it has points in the basin of attraction of an attractor on both sides, but it happens to be the same attractor. This case here, actually, oh yes, sorry, and the edge state here is the attractor within the threshold. This is a case where the attractor is actually equal to the threshold, so the edge state and the regular threshold are the same thing. This is an interesting case where we've got a threshold theta, we have an edge state eta, but in fact eta is the unstable manifold of eta on one side actually doesn't limit to an attractor, it limits to a saddle. So this would be maybe a slightly degenerate case. So in this case, the threshold lies on the boundary of just one basin of attraction, here on the boundary of two basins of attraction, and here on the boundary of three basins of attraction. So the paper, which I'm not going to go into, but probably Sebastian will do a bit more, that defines rate-induced tipping and in critical rates for non-autonomous systems where that limit to a compact invariant set of the autonomous future limit system that's not an attractor. So the critical rate means basically, yeah, your pullback attractor does not limit to an attractor in the future. And then we characterize the R-tipping edge state and the R-tipping threshold. Well, it's roughly speaking, it's what's going on here. So this is the R-tipping edge state. This is the thing that's important, the invariant set in the future limit system, and this is its stable manifold. This is actually the threshold that matters. But note that this doesn't necessarily correspond to thresholds of the frozen system. Okay. We also talk about, well, because you have already in two dimensions, you don't have this sort of well-ordering principle. You can have the possibility of a reversible R-tipping. So in particular here, at this point eta, there are two ways for this edge state. There are two ways that you can get to the attractor E1. You've got the short way and you have the long way. The long way corresponds to an excitable response. Yes, the definition for R-tipping, the critical rate in this general sense is a little bit technical, but you have yeah, I can't really introduce all of the notation in the time, but basically we have rates R1 and R2 such that R1 limits to some non-attractor and nearby R2 does not limit to that non-attractor. But that's a very weak definition of R-tipping. Generically, you have a much more sort of, a much nicer transversal motion from one attractor to another, and then codimension one, you hit some R-tipping threshold. So this is like a an example of an irreversible R tipping, where you have, this is the R tipping edge state, which is this eta plus. So that is an edge state for the future limit system. You have this theta of R. This is the R tipping threshold, which is the stable manifold of that edge state, or a forward invariant subset of it. So this is a case where you have two edge tails, we call them, that limit to different attractors. And in that case, generically, you will have an irreversible R tipping. In this case, you have two edge tails that limit to the same attractor. And in this case, generically, you'll have a reversible R tipping. And this bottom one is a degenerate case where the parameter variation is such that as we increase the rate, you come up, you just hit eta plus, and then you go back down again. But this is clearly something that will not be generic. Okay, we have a theorem which is a sufficient conditions for, in terms of the behavior of the frozen systems, to say there'll be an R tipping in that system in the non-autonomous case. It's we are quite far from having necessary and sufficient conditions, and I think it's one of those cases where already when you go to high dimensions, it becomes a numerical computational problem. I think I won't try and go through that. I will just go on to discussion and future challenges, so there's a bit of time for questions. There's a whole load of challenges for the future, including finite time notions of rate-induced tipping. What happens if you don't limit to things that are autonomous? Can you actually define something in that sense, or does it become is it no longer possible to have a sort of a qualitative definition of R tipping? There are different types of R tipping where you don't cross regular thresholds. So it could be you have irregular thresholds, codimension 1 stable manifolds that, in fact, for example, if you have in 3 dimensions, you can have a saddle periodic orbit whose stable manifold is a Mobius strip topologically. And that means that when you cross that thing, you don't go from one side to the other. There's only one side already. So that's one thing we haven't really worked out. Chaotic saddles, where you have stable manifolds that are fractal. Compact invariant sets, where your invariant manifolds are of codimension 2 or higher. So there is something which Hassan Al-Qayyum called invisible tipping, that actually is related to that. And then if you have a multiple timescale system, I think Sebastian talked about this probably last week and will in his talk later this week, we don't have thresholds anymore. You have quasi-thresholds. And then, yes, asymptotically constant external inputs, and there's a technical problem in terms of compactification. If your decay is too slow, then the limiting system can behave in a bad way. So that's something, and then external inputs that are not asymptotically constant. Okay, so I'd just like to thank some sponsors for this, and here's a list of the papers with some details that I was talking about, and I'm very happy to take some questions.
Thank you, Peter, for this interesting talk. Questions, please. Anyone is having any question? Yeah, then I'll start. I have one question. Peter, can you go back to your slide number 14?
Number 14.
Yes, this one. So this black solid and this dashed curves, so they are basically the attractors for the autonomous dynamical system, right?
Yes, so these are the attractors for the frozen system.
Only for the frozen system. So when there is no rate, right?
Yes, so the red corresponds to, this is what a typical initial condition does for the non-autonomous system. If you have a parameter shift that starts at -1 and ends up at +1. So if you stayed at -1 and you start with a cloud of initial conditions, say on X, they will all head very quickly towards X minus. And beyond that, you can actually, you can actually see the sort of the compactification going on here as well. You could actually write this as an autonomous system in terms of X and lambda. And if your lambda dynamics is very slow, you've got a timescale separation, and basically these will be critical manifolds. There'll be stable and unstable branches of critical manifolds. Don't know if that makes sense.
Okay, so basically when we are moving it fast, so that lambda will basically become a state variable.
Yes.
And
you
those
can think of it as a state variable, yeah.
State variables, and those then those curves in the bifurcation diagrams, they will basically become manifolds, right?
Yes.
Okay, okay. And then I have another question. When you have talked about this partial tipping in the case of let's say a periodic attractor, so you have that very nice video, so there is a limit cycle, and yes, there is this limit cycle, and so there is obviously a pullback attractor. In one case, when the rate is low, it comes out of the green limit cycle and again goes back. And but in the case of partial tipping, so not all of them goes back, right? So
yeah, this is the partial tipping case I've got running at the moment.
Yes, yes. So now my question is that I see it in the phase space, so that limit cycle, and some of that points goes back to the green circle. So now if I want to see the time series, how that time series will look like?
Ah, yes. So the time series, well, you can sort of, if you were to follow one of these blue spots around, what you'll find is that, say, and we plot out the Y, what you'll see is a periodic behavior, and then it sort of goes off a bit here and then comes back. But depending on the phase of where you are in the pass limit and where you are exactly on the cycle, as you get, if you like, the maximum change in the parameter, you may end up just going off to -infinity or +infinity or whatever, depending on whether you're looking at the X or the Y.
Okay.
I think, yeah.
Okay. Thank you. So, yeah.
So you talked about the trajectory that is in the intersection of the stable and the unstable manifolds. So is there any relation between the R-tipping and the explosion of the canard trajectories? Because we see these canard trajectories in the intersection of these manifolds.
Yes. There's a lot of connections between this and canard trajectories. If you start doing parameter shifts on a multi-scale system, yeah. So at the moment, what I've talked about here hasn't had a timescale separation within the autonomous system. But if you have timescale separation in the autonomous system, then the canard trajectories are really critical in determining where these quasi thresholds are. Yeah, and I'm sure Sebastian will talk about that in more detail.
Okay, so thank you.
If there are no more questions, then let us thank Peter for this excellent talk. Thank you, Peter.
Thank you very much for the opportunity.